Good afternoon, everyone. So, can you hear me?
Afternoon, sir, we can.
Okay. We will start the second lecture. So, last time we just touched the topic Bernoulli distribution. So, before that, if I revise your knowledge, we talk about exponential distribution. Okay. So, this exponential distribution is very much interested in your undergraduate projects if you do simulations to model the service times, waiting times, so that kind of time parameters. Okay, so now that is we called as continuous time distribution. Bernoulli distribution is not a continuous time. We call this is a discrete time distribution. So this is an experiment where you can have one of two possible outcomes. So if you if you do some experiment and you can have only two outcomes, for example, uh, when you toss a coin, so you have only have either tail or head, no? So that is two outcomes of one experiment. That kind of trial we call Bernoulli trial. So, for example, tossing a coin. So then if we come up with head, then we call x equal 1. Otherwise, tail, it is x equal 0. So x is the random variable. So last time we defined what is the random variable. The sample space is head and tail. So this sample space we map to a random variable. So if it is head, random variable equal to 1. If it is tail, random variable is equal to 0, something like that. So therefore, if the if the coin is fair coin, so then we can have this x equal 1. That means the head comes up is equal to 0.5 probability. The probability of having tail, that means x equal to 6 is 0.5. These things you already know. So then how you going to define the probability density function? But here we call probability mass function because instead of density we use here mass because this is not continuous function. So density we cannot use because density term density we use for continuous functions. Okay, this is the probability mass function. Px equal to 1 is p, then px equal to 0 is 1 minus p. If the coin is a fair coin, this p is equal to 0.5. So that means 1 minus p also equal to 0.5. The expected value, so expected value equal to p, the variance equal to p times 1 minus p. Okay, so then the probability mass function or density function looks like this. For example, let's say p equal to 0.75. So that means the coin is not a fair coin. Okay, p is equal to 0.5. Then you can see px equal 1 equal to 0.75. No, here, but this is 1 minus p. This is 0.75. This should be 0.25. So this is the probability mass function. And this is the notation for Bernoulli distribution. So always this T is for the expectation. Now binomial distribution. If you don't have any question regarding Bernoulli distribution, we can learn binomial distribution. Another discrete time distribution. Okay, another discrete distribution. So here. Now this is not a discrete time. Okay, I wrongly expressed. This is discrete random variable. It is not exactly time here. Why we call discrete random variable? This random variable x equal to 1 or x equal to 0. There is no x equal to 0.5 something because only we have two outcomes. Okay, so another third outcome we can't have. So this is impossible. That is why we call this is discrete. It's not time. So as a common term, I say time, it is wrong. Sorry. Okay, now this is another discrete random variable. So here also you can now see the random variable is a discrete value. So now here Bernoulli, you have only this parameter p, but in binomial distribution, you have parameter p and also simple n parameter. So from this description, you will understand very clearly the number of successes. Now look at very carefully the number of successes in n independent trials, each with probability p of success. Now, can you identify the difference between Bernoulli distribution and binomial distribution? There is a relation. In Bernoulli distribution, so this is an experiment where you can have one of two possible outcomes, either success or unsuccess. Okay, either win or fail, either head or tail, something like that. Here also, you have a random variable which has probability p of success. So that means success or unsuccess. Again, there is a two outcomes. In binomial distribution, also we have two outcomes, but we do n independent trials. Okay, we do n independent trials and then get the number of successes. That number is the random number here. Okay, so this number of successes has the binomial distribution, not this probability of p success. This is actually the Bernoulli random variable, this p, not p, the whether that success equal to p or otherwise the unsuccess equal to 0. That is the Bernoulli random variable. But what you do this trial n times independently and then get the number of successes. Okay, it looks like now if you toss a coin, you can have head, tail, let's say 5 times, head, tail, something like that. So here, simple n equal to 5. You have n dependent trials and each with probability p success. Let's say this success means tail, head. Okay, so here there is a probability p that you can have head. Okay, here also probability p. So these are independent trials. So there is a probability p that you can have success. Success I can name as head. Is not success, that is tail. Okay, so then how many success? Now you can see here 1, 2, 3. Okay, so this number 3 is the random variable, not this n, not this success. Okay, number of successes in n independent. This trial should be independent. That means there is no dependency among these trials. Okay. Okay. Now this binomial distribution probability mass function is given in this way. Okay. So how many trials? N independent trials. How many successes? This is the random variable I told. Number of successes. That means your random variable x equal to simple x. This is the number of successes. And this, this is the combinatorial. This will give combinations, number of combinations. Sankarana Sanyojana in A level, you know it. I can tell that this nx, this notation equal to NCR if you. And then this is success p, and 1 minus p is the other probability. So how many successes? X number of successes, and all other n minus x are failures. Okay, so this will give the probability that you can have x success. The mean value is given in this way. and variance is given in this way. So sometimes this 1 minus p we call as q sometimes. Okay. So instead of 1 minus p, you can have q also. So then, okay. So then this figure, you will see that for different success probabilities and different number of trials, the binomial distribution varying. Okay. So when the number of trials is very large, you can see it has this normal curve shape. Okay. But when the number of trials are less, then it is moved towards the left direction. And this probability having a number of successes will be with very high density when you have high p-value. Okay. Okay, so you can compare these three curves. It will compare different p-values and different n-values. You can get an idea about the probability distribution of binomial distribution. Okay, so this is very important distribution if you want to apply random variables into your MATLAB or whatever the simulation model. Okay, binomial distribution. So in machine learning also, this distribution is very important. Okay. Okay, then there is a relationship. The number of successes in series of Bernoulli trials has a binomial distribution. That is true, no? So when you have tossing a coin, not one time, but several times, so then that is we call actually binomial distribution. Number of successes in series of Bernoulli trials. Bernoulli distribution can also be defined as the binomial distribution with n equal 1. So here, if this number of independent trials equal to 1 mean, actually this is the Bernoulli distribution. Did you understand the connection? It is very clear, okay? From these two slides, you can understand. So if not, please put your questions in the chat box. Okay, so if you understood the concept, can we do this exercise? Okay, a die is tossed 3 times. Now this is a fair die. Okay, there is no any inclinations. That this is assume this is fair die. So it tossed 3 times. So what is the probability of no 5s turning up? There are no any 5. Now 5 is here. Okay, 1, 2, 3, 4, 5 this part. So this side will not came for all these 3 times. So what is the probability of no 5s turning up? Now you have to identify what is the random variable and what is the distribution. Then only you can calculate this probability. Okay. So whether this is binomial distribution or Bernoulli distribution, definitely it is not Bernoulli distribution because it has 3 trials now, 3 times. Then it should be binomial distribution, isn't it? But there are 6 sides, no? There is in binomial distribution we can have only like in Bernoulli distribution we can have only either success or fail, no? Only 2 outcomes, but here 6 outcomes. Can you apply binomial distribution here? If you can, then how? So think about and then give your answers. which distribution you are going to apply to find this probability. If you don't want to talk, then you can put in the chat box. Yeah, binomial distribution. But in binomial distribution, now there are 6 outcomes. If you toss a die, there are 6 outcomes. So how do you solve this problem? Yes. Yeah, you can talk.
Sir, we can assume that having having five in the dice is 1/6, and not having five is 5/6.
Yeah, that is correct. Yeah. So what you have to do, you have to assume the success as turning up 5, no? So you get 5, that is success. Otherwise, fail means you do not get 5, no? So not turning 5. So in that case, the p-value, that means probability of success, equal to 1/6, and q-value, that means 1 minus p, the fail is equal to 5/6. And then you have n equal to 3. There are 3 trials now. So then now we need the random. What is the random variable? The random variable is the success. That means x. Let's say random variable is x. Now we need x equal 0, no? Because we need no files turning up. So this is the random variable which we denote as the success. That means the turning up 5 value, side 5. So therefore, by using binomial, now this is a looks like a binomial distribution. So what you need, NCR, in P to the, let's say this is X, no? And 1 minus P n minus X, okay? So we know that n equal to 3, and this actually should be X, no? This is 0 now. P is 1/6 times again 0, and 1 minus p equal to 5, that is 3, no? Because n equal to 3, no? So what is the value for this one, no? This is roughly 0.578. Okay, so that means you understood the concept here regarding the binomial distribution. We will go to this example. So in very old days, there was a probability of 80%, 0.8 of success in any attempt to make a telephone call. So if you attempt to make a telephone call, there is a 0.8 success, but today's that success probability is almost 1. Not almost 1, it is very close to 1. But in old days, it was like this. Calculate the probability of having 7 successes in 10 attempts. This is very easy now. Everything is given. Okay. So what we need dx equal 7. random variable is 7 now. The number of success. This is equal to 10 C7. Out of 10, you have to have combinations of 0.87 and 0.2 to have 3, no? 10 attempts. All this. So in the exam, I will give only half marks for this because you have to give the final answer. Should be like this. Okay. If there are 10 marks, okay, there are 10 points. So this one you will get maybe 6 points. For this one you will get 4 points. Okay. So if you lose any of these steps, like this is the why I give more marks to here, because this is the concept and how you're going to apply them. But even though you don't know how to, even though you know how to apply the concept, but you don't know to get the correct answer, that is also not good. No? Final answer also very important. So therefore, you get 4 marks. Therefore, the exam, this kind of questions, you have to have those essential steps, all the steps. Okay. Now, how to draw a histogram? Now, for this particular example, okay, this particular example, there are 10 attempts. And then this is the probability of having 7 successes, 0.2. It is equal to 0.2. Okay, so these 7 successes with 0.2 probability. So this one we found. Likewise, if you find what is the probability of having no successes, 1 success, so then you draw this discrete random variable, you have this type of distribution. So we call this as a histogram of the binomial distribution. So why we have this discrete version? Because the random variable is discrete. Okay, the random variable is discrete because it can have 0, 1, 2, 3 up to 10. Okay. Okay, shall I move now? You understood the question? Okay, now we will move to our last discrete random variable, Poisson distribution. Some people say Poisson. Poisson, you know what is Poisson? That is some pronunciation, but most of the Europe and American, those people say this Poisson. Okay, not the Poisson. Poisson, you know, that is something else. So your some undergraduate and some research project presentations, we hear that term, but that is okay, but try to correct. Okay, so the notation is like this. So there is only one variable called lambda. Now remember these variables also. Now in binomial distribution, n and p, okay, number of trials and the success probability. But in Bernoulli, you don't need number of trials. You just need the success probability because number of trials always 1. But in order to define binomial problem, you need this n. Otherwise, you can't have this formula. No? Poisson distribution, only one parameter you need, that is lambda. Okay. So what is the description? So in which type of random variables we can have in this distribution? So here you can see arises out of the Poisson process as the number of events. And you can see number of events in a fixed time or space. Now we don't have, we do not need to consider this space now. We consider time, okay? Otherwise, this Poisson process we can have in the space domain also, you know, XY coordinates, graphical location. if you want to model users inside the location, then we can have this pause on process. Okay, but no need to consider that space part, but remember space also possible. But if you consider a fixed time duration, the number of events happening in that duration we can model as a pause on process. Okay, so events occur at a constant average rate. So the event occurring rate is a constant value, that is this lambda actually. Okay, event happening rate lambda. So if you know that event happening rate, you can find the probability of having x number of events during that time. Okay, so this x, simple x, is the random variable. This capital X is the random variable. Simple x is the specific value of that random variable. So what is that random variable? The number of events in a fixed time, given there is a constant average rate of happening that events. So that probability you can obtain by using this formula. Okay, so this is what we call Poisson distribution. The mean value is lambda, variance also lambda. So this is a kind of Poisson distribution when lambda equal to 3. So if you put lambda equal to 3 and for different x values here, now this k is actually you can consider as x. Okay, so when x equal to 0, always it is 0, then it has this kind of shape. Okay, so this is the same definition. The Poisson distribution x is said to be a Poisson random variable with parameter lambda if x takes the value 0, 1, 2 up to infinity. This is the probability density or mass function given in this way, the same. Okay, now this is for x equal to k. This is x equal to x, nothing different. Okay, if you understand the Poisson distribution in this way, I will come to this distribution again after defining this arrival process. Okay, so without knowing this arrival process, it is not sufficient to understand only this formula for Poisson distribution. Poisson distribution you can identify by using this formula. If you see this kind of pattern in any probability distribution, you directly tell this is a Poisson distribution. And this will give the number of events in a particular time, that probability distribution. But in order to identify the real meaning of random variable, you have to identify first this arrival process. What do you mean by an arrival process? So look at this diagram. So now here you can see this is the time axis. We don't talk about space domain, okay? This is time. So you can see when the time starts from 0 until S1, there is no any event. Now, when the time is equal to S1, capital S sub 1, there is an event. We call that event, let's say, arrival. There is an arrival. For example, in the Zoom lecture, so when I joined, so I am the only person, so there is no any student arrival. But after few seconds, one student join, I can see at this time. So after another few seconds, the second arrival also join. Okay, something like that. After another time period, the third arrival. So these are the arrivals. Arrivals happening at time S1, time S2, time S3. So at time S1, this NT equal to 1. So that this NT, capital NT is the counting number. Okay, NT equal to 1 at S1. Okay, NT equal to 2 at S2 because the second arrival also happened at this time. And at this time, the third arrival happens. So, okay. Then what are these capital X1, capital X2, capital X3 represent? Now, S1, S2, S3 represent the time instance we call time epochs, where students are arriving to the Zoom session. And capital NT represent the number of arrivals. So at this time, 1, here another one. So therefore it is incrementing. This NT always increment. If there is arrival, it will increment by 1. And what are these capital X1, capital X2, capital X3? Can someone reply? What are these X1, X2, X3 represent?
Duration. The logging.
Yeah, it is.
Interval time.
Sorry?
Interval time.
Yeah, it is duration, but what duration? It is the interarrival time. So between two arrivals, what is that time? Now between the first arrival and the second arrival, the time is this one. Between the second arrival and the third arrival, the time is X3. So these are we call interarrival time. Okay. Now you can identify here two things. You can identify here two things. So arrival process is a sequence of increasing random variables. Now arrival process is a sequence of increasing random variables. So this S1, S2, these are the random variables. Okay. So when there is an arrival, we map that arrival into a random variable. So S1, S2, these are random variables. And the interesting thing is this Fn always less than the Xn plus 1, no? Because these are increasing random variables. So if S2 cannot be less than S1 in any point. And the other thing is here we assume there is no simultaneous arrivals. Okay, let's say from the door which people can arrive, at a time only one person can enter through that door. So therefore there is no two people can come at the same time. So no simultaneous arrivals. So assuming that these S1, S2, S3 are always increasing random variables. Okay. And so that is why we call like this. Si always less than Si plus 1. You can't have here less than or equal. Okay. It cannot be equal because there are no simultaneous arrivals. So this is always less than notation. So that means Si plus 1 minus Si, which represent the interarrival time. No, so you can see this is the I plus 1 arrival happened at this time, and this is the previous arrival. The difference is a positive random variable which represent this capital X. Okay, which represent the capital X. So therefore, this capital X also a random variable. Why? Because it will give this capital X is obtained by subtracting this S2 by S1, S3 by S2, like that. So that is also a random variable. So S1, S2 are called arrival epochs, multiple arrivals can't occur simultaneously. Okay, so this is very easy to understand, this arrival process. So there are many applications, okay, not only in data communication, but this is almost applied in data communication. So in telecommunication, you know, when you model a telecom system, there is a network. So users are arriving or they are requesting the resources from the network operator. Then that user's arrival process can be modeled by using this kind of arrival process. Okay. Now, what are the two processes inside this arrival process? One is this NT. Okay. So NT is the number of arrivals up to and including time t. So NT always an increasing random variable. The other random variable is the interarrival time, x1, x2, x3. So that x1 equal to s1, x2 equal to s2 minus 1, something like that. So you can have interarrival time as one process, random process, and the counting process is parallelly going with that interarrival time. So whenever there is arrival happen, this NT is incremented. Okay. Any question? Okay. I think I will come to this part later. So this slide is important here. Poisson process definition. A renewal process. Sorry, a renewal. Okay. Renewal process is an arrival process for which the sequence of interval times are. Okay, you can't have this one time because you don't know this part. So I will come to here. The Poisson process is an example of an arrival process. That is true now. Now you know Poisson random variable, you know. Now we are not talking about that random variable. Now we are talking about the process of Poisson. Okay, Poisson process. So it is an arrival process. Then you know what is an arrival. A Poisson process is a simple and widely used stochastic process for modeling the times at which arrivals enter a system. Even a shopping center, when the customers are arriving, that can be modeled by using this process. For the Poisson process, arrivals may occur at arbitrary positive times. So this S1, S2, S3 until Sn, those are the arbitrary time instants that arrival can happen. More convenient to define a Poisson process in terms of the sequence of interarrival times. So x1, x2, x3, these are the interarrival times. So by using interarrival times, we can define this Poisson process. They are independent and identically distributed. These x1, x2, x3 are independent and identically distributed random variables. So what is the meaning of these two? These random variables are independent. So that one you can identify, okay? They are independent. So that means the first arrival happened. Is there any impact on the first arrival to the second arrival?
No, sir.
No, because users are independently joining the system. But we can't say that, for example, this Zoom class. So when one person joins, maybe he will tell his friend, okay, the class has started, please join quickly. So then there is a dependency, no? So that type of things we can't model. Then they are not independent. Let's say the Sachinta came at S1 time, then Tivanka came at S2. So because Sachinta called Divanka to come quickly. So that is dependent, not that type of cases. Okay, so we can say, oh, let's say there are 100 people. Those 100 people don't know anyone. Then they are joining independent. So that is the meaning of independent random variable. Okay, there is no any dependency of x1 to x2 to x3, but they are in. And what do you mean by identically distributed? These x1 and x2, x3 are independent and also they are identically distributed. That means they are identically distributed. Now let's say this x1 is a random variable which follows Poisson random variable, which we explain here, Poisson distribution. Okay, so this x random variable, this x1, okay, this x1 is following the Poisson distribution. And remember, this x2 also follow the same Poisson distribution. X3 also follows the same Poisson distribution. That means x1 follow Poisson and x2 exponential, x3 binomial. It's not like that. So all the x1, x2, x3 random variables are following the same probability distribution. So that is why we call they are identically distributed. But they are independent. But the values are coming from the same distribution. Okay, a set of variables is independent and identically distributed if the variables are all mutually independent. The variables are all drawn from the same probability distribution. I think that is clear for you. This IID. I think this term you heard during your the random variable courses. Maybe you have forgot the meaning and the concept. That's why I revised this. Okay, now what is a renewal process? Renewal process is, and it is a arrival process. It is an arrival process for which the sequence of interarrival times is sequence of independent and identically distributed random variables. Okay, now you can see type of. Now you have total domain. Let's say this is arrival process. Okay, inside arrival processes we have subdomain we call renewal processes. Okay, renewal processes. So what is why we can't have renewal processes same as arrival process? Because this is a particular type of arrival processes where the interarrival times, that means this x1, x2, the interarrival times is a sequence of independent and identically distributed random variables. Maybe there are some other processes, they are not independent and identically distributed. So then they are not renewable arrival process. Okay. So here, all the interarrival times are IID random variables. So then only we can tell that arrival process as a renewal process. Okay, then Poisson process is a renewal process. Now, if you the Poisson process, a subset of renewal process. Okay, so how we extract the Poisson process in which the interarrival intervals have an exponential distribution function. Now I told that this renewal process is an arrival process, but the interarrival times are independent and identically distributed randomly. So that means the interarrival time should follow the same distribution, same random distribution. It can be Poisson, it can be exponential, it can be by whatever the distribution. But if that interarrival time distribution is equal to exponential distribution, then we call that process as Poisson. Okay. Now, remember, we learned about this exponential distribution. If I go to that slide, exponential distribution, it has PD, probability density, lambda times e to the power minus lambda x. So this type of PDF we call exponential distribution. Now, in our arrival process, if those interarrival times x1, x2 follow this distribution, then we can have that one as a Poisson process. Okay. So Poisson process is a subset of renewal, and renewal process a subset of all arrival process. Did you understand? Now, without having that previous knowledge, I think you may confuse, no? That is why I spent the previous lecture to revise all the probability distributions. Otherwise, you can't catch the idea properly. You can, but you need more time. Now I think you no need to spend a lot of time to understand these things after this lecture. Everything is given, the conceptual thing. Okay. Now Poisson process we define in this way. Okay. This is the exponential PDF, and this lambda is the arrival rate. Why we need arrival rate? Because this Poisson process is a renewal process, and renewal process is a arrival process. So arrival process has some constant arrival rate. Do you remember that one? Maybe now you don't remember it. Here we mentioned. Yeah, here we mentioned, no? Events occurs at constant average rate. Do you remember? The events occurs at constant average rate. That is lambda. So that lambda reflect here. Okay. Now if lambda is greater than, that means positive value greater than 0, it's a fixed value. The counting process NT. Okay. So you know what is this counting process? The number of arrivals you are counting is called a Poisson process with rate lambda, and this condition should be satisfied. So N0, that means at time equal to 0, the number of arrivals should be 0. So that means at the very beginning, time equal to 0, when the system starts, the number of arrivals should be 0. There is no any arrival at time equal to 0. And NT has independent increments. Why it is independent? Because these are independent and identically distributed random variables, the interarrival times. The number of arrivals in any interval length tau has Poisson distribution equal to lambda tau. Now look at this diagram. Now I am going to find the parameter this pk tau. That means the probability of k arrivals in interval of duration tau. Okay. So if you consider a duration of tau, now let's say tau equal to t1. So during this duration, during this t1 time, what is the probability of k arrivals happening? So this is important. No? So in a telecom network, so during a particular hour, let's say 2 p.m. to 3 p.m., what is the probability of having 100 customer arrivals? to the main switch. What is the probability of having 100 arrivals customers? That type of probability is very important to calculate in order to plan your network. So network, now you know network planning, you need this type of process handling for network planning. Okay, now, so what is the probability that k number of customers arrive in that duration? So that is we call the probability we denote as k tau. And we call this process, this Poisson process is time homogeneous process if this probability does not depend on the time duration tau. That means now one duration you can take from here also, let's say t1. So what is the probability of having k arrivals during this t1 time, and what is the probability having k arrivals during this t1 time? Now this t1 time duration we pick up in different locations in the time axis, but we need the probability of having k arrivals in the same durations. Okay, so are these probabilities, these two probabilities are same in practice? Are these two probabilities same?
They are not same.
Yeah, in practice they are not same. You're correct. In practice they are not same. For example, now let's say this T1 is the 1 hour duration, and if you took this 1 hour during morning time, let's say 10 a.m. to 11 a.m., and then you took this T1 duration in the early morning, like 1 a.m. to 2 a.m. So many people are sleeping now. So then these probabilities are not same in practice. Okay, in reality they are not same, but somehow if these probabilities are same, it does not depend on the time duration tau where we pick up that duration, then we call that process as a homogeneous process. Okay, homogeneous Poisson process. So if this time homogeneity, if we assume time homogeneity, that means even though you pick up this t1 time during any 1 hour time, that probability of k arrivals is same. But in reality, it is not. The number of arrivals in disjoint time intervals are independent. Now, this is t1 time, this is t2, t3, like that, tm. So during these are disjoint time, so they are not overlapping. Okay, so disjoint time intervals and the number of arrivals are independent. They are independent. Now, these are some kind of assumptions and also properties. The small interval probabilities. Now, let's say this tau is very small value. So this is like delta, this type of. Now, tau equal to delta. This is a very small time interval. Okay. So what is the probability that you can have more than one arrival? So if you select this delta time, very small time, let's say maybe you divide maybe microsecond level or nanosecond. So it's a very small time interval. So what is the probability if there are more than one arrival? That means 2 arrivals, 3 arrivals. So that is 0, no? Why? Because we assume in Poisson process, there are no simultaneous arrivals at the same time. So if you select a very small time interval, nanosecond level, very small, so during that is like a very small time instant. So that time instant, you can have at most only one arrival. There are no simultaneous arrivals. So therefore, k greater than 1, that means more than one arrival probabilities, we can say 0. So what is the probability you can have exactly one arrival during that delta time? So this part needs some mathematical knowledge to understand. Now this lambda is the arrival rate. For example, lambda equal 10 means, this means 10 customers or 10 arrivals per 1 second. 10 arrivals per 1 second. So if in the time axis, if you have delta time, so how many arrivals will come here? So for 1 second, it is 10. Then for delta second, it should be 10 times delta, no? It should be 10 times delta. That means lambda times delta. Okay. So during this delta time, the arrivals can happen lambda times t. So that is, but when we have this delta is a very small value. Let's say this type of seconds, very small. So at most we can have only one arrival during this time. Do you agree with me? During a very small time interval like this, you can have at most only one. It can happen, no? One arrival can happen, but no 2, 3 arrivals, because this is very small. So at most we can have one arrival. But what is the probability? Now, during 1 second, you can have lambda. So during delta second, you can have lambda delta. So that is that probability. Okay? Lambda delta. Now, what is the probability that you don't have any arrival? That means k equal to 0. Now you know k equal to 1 probability, lambda delta. K greater than 1 probability 0. K equal to 0 probability, then it should be 1 minus the summation of these two, no? Because we can have only these three cases. Either k can be 0, 1, or more than 1, because k cannot be negative. If you know these two, and there are only these three cases, then this probability 1 minus lambda delta. Because of this condition, the total probability equal to 1 for all cases. Okay, so I think this section, this part, you can understand how these values comes. Okay. So any problem? Okay. Now we will. Now the time is over, no? Okay, I will stop from this point, because if I started this, it takes like 5 minutes. So any question regarding Poisson process? Now today we described the Bernoulli trial, binomial distribution, Poisson distribution, and the total arrival process I described by using different random variables. There are 2 random variables here, interarrival times and the number of drivers NT counting process. And then we describe what is a renewal process, and then what is a postpone process, and how we obtain the postpone distribution probabilities here. So I think Wednesday also you have a lecture, but the thing is I have a my final course, staff teaching course. There is a final session in this Tuesday and Wednesday. So I cannot conduct lectures during those 2 days, and most probably Thursday, if Dr. Chandana will not take that introduction to research lectures, there are 2 lecture hours. Okay. During that lecture hours, I will take DSP and ADC lectures. Okay. So I will announce it in the LMS, and then I will send an. Now there is a WhatsApp group in. So I will send those details to Sachin and the WhatsApp. Any question?